Okay, last time we talked about a hash table, okay, hash table. And then we talk about one problem in the user code for the hash table. Okay, so the hash table's purpose is to create a content addressable memory or reverse array, right? We actually talk about it. We jump into the searching and hashing part. Okay, this one we have done. Now we are going to move on to the next topic. So I told you guys before that this is data structure course. We will be on topics. Okay, basically topic by topics. So first one, we talk about a reverse array and solve the problem like that, okay? Next one, we don't talk about sorting. Sorting, we already covered it before. So next one, we are going to cover it for another one that's before we go into the parsing tree, okay, we are going to talk about tokenization first, okay? Tokenization and stack, use of stack. So we will talk about this balance parenthesis and the stack and the token tree and postfix and infix expression. Okay, these are the topics we are going to cover starting from this week. It may take 2-3 weeks to finish it. Okay, it may take 2-3 weeks to finish it. So these are topic. These are also important topic in data structure. Okay, so let's get started. First, I'm not going to 100% follow this course. Okay, so what I want to do first is that let's look at a course I'm teaching at Dewey University. This language. This course is called Programming Language. I told you that level 4 programming. Level 3 is data structure and algorithm. Level 4 is this programming language. And you'll be on the structure and interpretation of programming programs. Okay. And this one actually in Berkeley, this one is the first programming course, CS51A, CS61A, structure and the interpretation of computer programs. Okay, this is a course structure and interpretation of computer programs. So what we want to learn from here actually is the use of the program to do tokenization. Okay, and then to do basically to syntax analysis. Okay, so these are the purpose. And then data structure is used to support it. We are going to talk about the data structure to support it, including the stack. Okay, and to do finish these several chapters. So let's look at what are these. Okay, let's look at what are these. So first thing is that let's use this one as a short introduction. So basically, there are many programming languages. Okay, and this different family of the programming language. You all learn some of the programming languages. Then you need to do some different kind of programming paradigm. Some is on the functional programming, some object-oriented programming, some functional programming. Okay, whatever. These are not important. And then your program, sometimes you need to do translation. So you do translation for C++ language Java language and Python language. Okay, so you have the compilation that translate one program to the target program. Okay, you may also do hybrid. You may do the interpretation, so sentence by sentence, question and answer as an interpretation. Or you may have mix, that do a virtual machine, translate the front end by the compilation, back end code generation by the interpretation. Okay, this is the virtual machine. So these are the basic translation for the computer programs. And then in the compilation, okay, we jump ahead more. In the computation, we actually have 6 stages. So lexical analysis, syntax analysis, semantic analysis, machine independent analysis, and then machine dependent improvement. Okay, these are different stages in compilation. So why this is so important right now? Because nowadays you do have AI, okay. So your AI translate from one language to the other. Say you translate from your English to Spanish, okay? Or translate from some sentence and you create your video right away. So this actually AI nowadays become a parser, front-end parser or front-end interpretation for an AI program. So this language translation is very, very important now, okay, nowadays. Okay, so but the first few stage is to use for the scanner and the parser, okay? First few stage is used for the scanner and the parser. Okay, so these are the basic introduction. So first one is the lexical analysis. That's called scanner. So scanner, the purpose is that you do have your language, say if and parentheses a equals 3. So scanning means that you actually tokenize this as if. That's one token. Parentheses, that's one token. A, that's one token. Double equal sign, that's one token. Okay, so you actually, this is tokenization. You actually convert each symbol into the letter that the computer or the word that computer pick, and that we call it tokens. Okay, nowadays the AI also count the number of the tokens. Okay, so in order to do that, you need to use something called deterministic finite state machine or DFA to do it. Okay. Okay, that's the first stage. Today we are going to cover this finite state machine. Okay, we'll talk about this finite state machine. And then the coding for finite state machine. And then the second one is called syntax analysis. First stage is called lexical analysis. Okay, lexical analysis is token out the tokens. And then syntax analysis is token out the syntax. So you know that equals and two operator A and 3. This is actually variable. This is actually constant. So we create a sentence of variable, verb, constant, verb is equal, okay? We create a syntax tree like that, okay? This is called syntax analysis. So basically, there are 2 stages. One is to do tokenization. One is to do the syntax analysis. Okay, syntax analysis need to have the push down automata including a stack. Okay. Okay, and these are the first 2 stages. The scanner and parser use in the compilation. Okay, and we need some data structure and algorithm. So today we are going to focus on the first stage, tokenization. Okay, any question?
Nope.
No, no question? Okay. So this is that, but we are not going to follow chapter by chapter. So I'm not going to cover, this is the first chapter, okay? But we will directly jump to the chapter 10. Okay, this is chapter 10. For the same course, we directly jump to chapter 10. That's called lexical analysis tokenization. Okay, let's look at this one. So tokenization is that you read in symbols, symbol by symbols, A, B, C, whatever, and you start to study and you generate token. Okay, so for example, you actually have this one if A equals 3, curly brace, and something, curly brace. You will tokenize it as this one as keyword, this one as parenthesis, this one as variable, this one as the operator, this one as a constant. Okay, so this is called tokenization. So you take in the symbol one by one, okay? And you need to understand what is the syntax diagram. This is what we will teach you today. And write regular expression, and then doing tokenization using regular expression and write a program for it. And using data structure for it. Okay, that's the purpose that we have today. Okay, so let's look at overview of the tokenization. So tokenization is the common task for data science come across when working with text data. Okay, so most language, natural language processing would need to have the tokenization now. Okay. Okay, and then in your Java language, we do have the scanner, right? We do have a scanner, and scanner is used to do tokenization, to tokenize word by word. Okay. So that's called lexical analysis. Okay, so your tokens being broken down into words. Okay, and then you want to verify whether it's a legal word or not legal words. So to check if your word is legal or not legal, we call it lexical analysis. Okay, so basically it is not cool that ping pong is not included in Rio 2016. You'll be tokenized into IT, NOT, COOL, THAT. Okay, these are different tokens. So one token is similar to a word. Okay, and you need to use some sort of criteria to determine these are different words. That's called tokenization. Okay. So you do have some text coming in, you tokenize it into different words, and this different word being built into linguistic module, and then from content to the ID, content to ID, so this build a dictionary to do inverted indexing. So these are the basic pipeline in the AI, okay? Okay, so these are the analysis. Let's go ahead a little bit furthermore, okay? So these are what you need. So let's look at the tokenization. So simplest tokenization is by the split function. Okay, so by split function, you actually chop it by using the space or the end of the string. You use that, okay, to do chopping. But this one is too simple, but sometimes your end of token is not space, sometimes it's comma. Then this split function will not work. Sometimes it's parentheses and A, there's no space. So this kind of tokenization will not work. Okay, to avoid that, if you still want to do split, you can add extra space before and after this parentheses. Then you can still use split to do tokenization, but this one is not a very good solution. Okay, this one is not a very good solution. We'll talk about how to do this kind of the tokenization without using the split function. Okay, but right here, I'm just talking about a basic tokenization can be using the split function to finish it. Okay, this part we suppose that we already teach you in Java, so we don't repeat it again. Okay, we don't repeat it again. Okay, so the advantage is easy. Disadvantage is that the file is big, the memory limit issue, whatever. Okay, that's actually okay. So you can tokenize it, but sometimes you will have extra comma in there. Okay, period. This should not happen. Okay. Okay, so that's line by line tokenization. That's the first one. That's actually using split. Next one is the line by line tokenization. You read in the whole line, and then you are actually analyze the line one by line. Okay, that's another way you can do it. Okay, but we don't discuss this. We actually should be fine. So what we want to do is that let's do it by regular expression or non-deterministic finite state machine. So how to do it to design a scanner? Okay, so you basically want to do lexical analysis. Okay, so if x equals 5, you generate this. Okay. So let's look at a simple example to demonstrate how to do this kind of the tokenization. So first thing, let's define something called natural number. Okay, so what is a natural number? Natural number is from 1 to infinity, right? Any number that's actually greater than 0. Okay, this one in terms of symbol, it will have at least 1 to 9, one of the symbol in 1 to 9, followed by 0 to 9. How many of them? Maybe 0, maybe in infinity. So it actually can be written by 1 to 9, and then followed by 0 to 9, and using a star. Star means that 0 or more. Okay, this is called natural number. Is that okay? Is that okay so far?
Yeah.
And this is called what? This is called SDD, okay? SST, syntax diagram. Okay. So you write down your syntax and then you parse your language by the syntax. This is called lexical analysis. Okay. So you start to see a lot of letters and you try to parse it. Okay, you try to parse it. This is called syntax analysis. Okay, and we can build a tokenizer using hand to write it. Okay. And you can determine what is an identifier, what is a constant, what is a command, what is a symbol. Okay. It's called ad hoc scanner. So ad hoc scanner is like this. When you read in the calculator language, you start with the state one. If you see a parenthesis, you go into here. Okay, it can be left parenthesis, it can be right parenthesis, can be plus sign, can be minus sign, can be time. Okay, this actually you go into different languages. So if you see a parenthesis, that's left parenthesis that already can token out. So you got a circle. Then that will be token out. After token out, you go back to state number one to receive new symbol. Okay. So if you see a number, you go to the number here. And then if you see another number, it actually is repeating the number until you see a space or you see a end of string. Then you finish a number. Or you see a dot, you go to the second number, then you may have 3.4. You finish with another space, you determine that's a number, but that's a fractional number. So this is syntax tell us how to determine a symbol, okay? How to tokenize a symbol. Okay, so here we do have a Python version of the scanner that can do lexical analysis for divide, left parenthesis, right parenthesis, plus sign, minus a sign for different one. Okay, so they do have a program, and you read in the sentence line by line. Okay, and do analysis for it. Okay, and you analyze the language. Okay, this one is in Python. We do not want to so this one actually, let's assume that we actually read in A equals to 1, B equals 2, C equals A plus B parentheses. You will be tokenized as A colon equals 1, and then B colon equals, and then 2, and then C colon equals, and then parentheses, and then A, and then plus, and then B. And then the token type will be ID assigned, number ID assigned, number ID assigned, left parenthesis, ID plus ID parenthesis. So these are from original symbol to token, original symbols to token, original symbols to token. Okay, as for this token, how it can be calculated or doing anything else, that's later stage. Okay, but at this moment you can do this and you can successfully tokenize. Okay. Okay, so first thing is that we can do tokenization by using the finite state machine. So you provide your input language and grammar. You use the grammar to determine how your language can use the finite state machine to create your token tree. And your token tree evaluated by the program, it becomes your program's language code or object code. So this is the whole process for compilation. So far, okay? So far, okay?
Yeah.
So we learn data structure and the language rule and recursion and the data structure just because we want to learn the grammar. We want to learn the state machine. And we want to learn the token tree. So this is tree structure, this one is graphic structure, this one is rules, okay, grammar rules. So data structure and algorithm are a supporting course for programming language because of that. You need to learn data structure in order to support every single step and content for language translation, okay? Okay, so this is the purpose to do this, okay? This is the purpose for doing data structures. Let me copy this page. Give you this page, okay? These are the purpose for using the doing that. The purpose of language translation. Now let's look at the simple finite state machine, okay? Let me jump to somewhere. Okay, so a simple finite state machine is that you read in one character and you have your state. You read in one character and determine which state it should go based on the later. So this one is a basic state machine structure for C program, okay? So we will later use this algorithm to develop our finite state machine. And then try to give you an example to know that what kind of the application this finite state machine can do, okay? And this is used to, this is a driver program to talk about a table-driven scanner to do this, okay? Okay, before we jump into that, let's look at the syntax diagram, SDD, okay? Syntax diagram. So a syntax diagram is that before you analyze the language, you need to know about extended Baker's norm form, okay? It's called EBNF, extended Baker's norm form. So this form is used to describe your grammar. Okay, it is very simple, okay, not really hard. So before we go into that SSD, you need to know about OR operator. So a symbol can be A or BC. BC means that B followed by C. Okay, so this legal symbol can be A or BC. Okay. And this one means that A or B followed by C. So you have an A first or B first. You can only have one of them, but either one of them may follow by a C. Okay. This one is a OR and a concatenate. And there is an optional B. Okay, optional B means this one, you have A followed by C, but in the middle you may have 1 or 0B. Okay. And you may have curly brace B that actually, this one is 0 or 1B. Okay, 0 or 1B. This one is actually 0 or more B. Okay, using curly brace. So these are the syntax diagram by grammar, by graphics. Okay. So first you need to learn about this to describe your language. So your every single language can be used for these grammar items to describe it. C language, you can do this kind of syntax diagram. Java, you can also do this syntax diagram, okay? So digit is any one of the symbol 0 to 9, okay? Integer is a add operator. You may have a plus sign or no plus sign followed by many digits, followed by one plus digit. This is one plus, at least one, but one plus digit. Okay, this is integer. Integer means including zero. It can be zero to any number. Okay, this one is actually positive integer. So a number is either real or integer. And real number is plus sign plus a digit 0 to 9. Okay, this is digit, followed by a decimal point, followed by 0 or more digit. Is a real number. Okay, so these are different definitions for different numbers. So basically, before you actually qualify for a syntax, you need to draw down the language that you allow by the finite state machine. Then you implement the finite state machine to achieve the tokenization purpose. Okay, so translation is the purpose. Finite state machine is the tool. Finally, you write program to implement the scanner. Okay, that's the whole process of designing the software. So first, you need to know about regular expression. So you need to know about what is a legal email address. So email address is defined by this. Okay, defined by this one is a character. Okay, character followed and also the special characters plus sign means one or more of the character or the special symbol at one of the character, one or more that these A to Z letters, okay, repeat to 2 to 4 possible letters. So this one is something like equal at Louis u.edu. Okay, so this .edu is this portion. This Louis is this portion. This portion is my email name, username. Okay, so this one give you the regular expression for username as domain.qualifier. Okay? Any question? Any questions so far? Sherry, are you okay?
Yeah.
So these are the username. So this actually is used to qualify whether your language is following the regular expression or not. Okay, to see if it's an email or not. So let's design a simple. Let's jump ahead. Okay, don't talk about this. Let's look at a real example. Okay, let's look at the example. So this example is to write the legal use of the language Let's assume that let's look at this one. What is the legal representation for clock? So this one, 1:30 p.m., 23:11 a.m. Okay, this one is legal, this one is legal, this one is not. This one is legal, this one is legal, okay? For the time. So let's look at ending part. The ending part, you may have AM or PM. So A or P followed by M. So this portion is okay. This one handle the AM or PM, okay? And then you have a digit. Okay, this one is actually 0 to 5 followed by digit. So this one starting from 00 up to 59. Right? So this one is minutes. Is that okay? Hello, is that okay?
Yeah.
This one is the column, so this one is the middle column. And then you have this one 0, 0, 2, 3, 4, 5, 6, 7, 8, 9, and then 1 followed by these. So this one means this one question mark is 0 or 1 time. So basically this is representing 0 to 10 and 11. These are the legal hours. So it's 0 to 11 followed by colon, followed by 00 to 59, followed by PM or AM. This is your legal representation for the hour and minutes. And we can use a Python code and using regular expression to verify it. Okay, today we are not going to teach you how to write Python program to verify it. We are going to write C program without using regular expression to verify the numbers. And we will use the finite state machine to do it. Okay? Any questions so far?
No.
No? Okay. Okay, next one is a phone number. So phone number, you may have 510 304 and then 9428. Okay. So this is area code, regional code, dash your number. So normally you have 3-digit followed by a dash followed by 4-digit. Okay, this is your phone number. And long distance call, you may have 1-800. Okay, so like this. Okay, so you want to write a regular expression for it. Okay, so this one is a phone number's regular expression. If you draw the regular expression, you have 4-digit like this. Okay. And then there's a dash. And then there's original code, 3-digit. Okay. And then there is a area code and 1 area code. Okay, so these are the format used for regular expression to write a phone call. Okay. And then you may have simple integers format. So you have plus sign, minus sign, okay. And then you may have a 0 or 1 to 9, followed by 0 to infinity number of the 0 to 9. These are integer. Okay, these are the diagram for integer. Okay, anyway, we have enough. We have enough to talk about the different grammars, okay? So your different language will use a different grammar to qualify for the legal symbols. And here we do not intend to go over different kind of every kind of symbols, okay? Our goal is to show you how to design the first state diagram and first interpreter, okay? So that's the first job. Before we go into the second task, we will go into the course to look into the parentheses and the implicit postfix translation. Before we go into that, we'll go into the finite state machine first. Okay. So before that, we will actually look into our coding first. Going back to the previous chapter, we go back to the previous chapter to look at this scanner, basic scanner program. Okay, this basic scanner program. Okay, we may not, we can read the data from a file. We can also read it from a stream. So today, before we go into the file, let's just use a stream to finish this state machine. Okay, let's look at a program that can do it in this to process the text in the state machine. And we'll talk about the finite state machine. Okay. So let's create a program for it. So this one we will call lecture 3. The data topic we will talk about finite state machine. Okay, we'll talk about finite state machine. So this finite state machine, okay, again, what is a finite state machine? Finite state machine is to take your input language your Java program or something, to qualify it by the grammar, and using finite state machine to translate it to some target code. This is the whole purpose of language translation. Okay, so we are assuming that you provide some sort of input in string format. Okay, so let's get started from there. So let's create a first one that's called state.cpp. Okay, the finite state machine. So I call it state.cpp. So that's include okay, let's actually get started from here. So we will read in a string, but right here I don't actually read in a string. Okay, I actually just create some program that has a string. Okay, called buffer. Okay. So at this moment, that's don't read it in yet. Okay, let's just take in some of the words. Okay, let's assume that we do have a 1, 2, 3. Okay, then let's have the integer. Let's see, what that has a an integer called pointer. So we'll do chapter by chapter scaling, okay, until it run out of the buffer, okay? So every time your P will increase. Okay, so you are going to go over every chapter one by one. Okay, you are going to go over the chapter one by one. Let's go back to the state machine part, okay? Okay, so every time you actually read a next chapter, okay, and you try to use the chapter to go to the next state. Okay, so right here we read a new chapter, so let's assume that this one is a chapter CH, okay, equals above that at the P, okay? So you read one chapter, and depending on this chapter, you will go to the next state, okay? Okay, let's do nothing, okay? Let's just do this, let's do C out. Okay, let's directly just print it out, okay? And this one, let's see. So there are several characters. You have zero, you have space, 1, 2, 3, space to finish. So this first version of the state is just like that, okay? Okay, this is no problem, okay? This is no problem. We do not actually have the state machine yet, and we do not do anything yet, okay? So this one is okay, but we do work on this, okay? That's okay. Now let's add the state machine in, okay? So in order to do the state machine, we will need to know about what kind of the number we want to achieve. So here, let's go back to the finite state machine. Let's call it numbers. So let's assume that we started from initial state as actually 1. So this one state, if you look at if it is actually a space, initially you enter a space later. You will repeat the state. So this is state 1 actually is a standby state. Okay, you have standby state. You have nothing in there, okay? You have nothing in there. Okay. And then if you look at if you have some sort of a digit from 1 to 9, you go into the state number 2. Okay. And if you have if you get a 0, if you get a 0, you go to stage 3. Okay, because we want to have a natural number. If you in standby state, you see a 0, means your program will stop and you will have error. You have see a syntax error because 0 is not allowed in the finite state machine, in the natural number. It cannot be the leading number, okay? Okay, so actually, if you see a 0 in the standby state, you actually go to stage 3 and you actually say it actually is an error. and your final state machine start. If you go to the stage number 2, you see actually if you see 1 to 9, you go to the stage number 2, state number 2. Okay, so at 0 you enter into a error, or you see some sort of non-number. So actually anything non-numbers, for example, like you see A to G later, you will also say it actually is error. So you go to the 1 to 9, you go to here, right? You go to stage 2. So if you see a 0 to 9, you will repeat stage 2. Okay, you see a space, you go back to your your original standby state. Okay, so let's assume that we don't have A to G yet. Okay, because A to G may make things too complicated. Let's just assume that we only take 0, 1, 2, 0 to 9 digit. Okay, and we have 3-state finite state machine. Okay, let's just look at this simple state machine part here. Okay, let's consider this a simple case. So we have to have 3 states. Okay, that's assuming that we have only these 3 states. Okay, so here we may have another variable that's called state. Initial state is equals 1. Okay, so based on your state and your, okay, this one state is also an integer. Okay, so based on your state and based on your state and input, you will work on the machine. Okay, you will actually determine your where your next state is, and based on your input. Okay, so if you are standby state, okay, state equals 1, you are standby state. Okay, in your standby state, you may have 1 or 0. So if your input is, so if your character is the 0 character, then what will happen is that your state will equal 3. So you go to the stage 3. Okay, if you are going into the stage 3, we will do cout, and then you will say syntax error. Okay, and then enter. Okay, if your character is not actually 0, so if your character is between 1 to 9, this is a legal character, you will go to state, 2. Okay, so if you go to your stage 2, let's see. Okay, and right now, if you have, okay, another one, we do not say it, but this one, you will have else stay, actually, your chapter equals actually a space. This one, you will stay in state 1, but here we do not say anything because what happened is like, what happened is we don't go to the next state, okay? We don't go to the next state. We actually go to still stay in the state number 1, okay? We still stay in the state number 1. Okay, then if you are actually in state 2, and then if your chapter is less than equal to 0, and chapter h greater equal to 9, I'm sorry, h greater equal to 0, and then less than equal to 9, this one means that you are still within the word. So this one is to stay in state 2. Okay. Else, if the chapter equals space, your state will go back to state by state. Okay, anything else, you will go to state 3, error state. Okay. Okay, so each one of them, before you go, let's actually print out. So let's print out your chapter. And state. Okay, print out the chapter and state, and determine the next state. And right here, let's see, right here. Okay, so let's save and let's go. Okay, so initial state, you are at state 1. Okay, you read in a space. So you repeat state 1, no problem. And then in state 1, you see a 1, so you go to state 2. And in state 2, you actually see a 2. So you repeat state 2. In state 2, you see a 3, you repeat state 2. In state 2, you see a space, you return to state 1. Okay? And then you actually go to In the state one, you see a space, you remain in state one. Okay, so this actually is a good execution of the finite state machine. Is that okay so far? This is simple finite state machine so far. Okay, we haven't used it for syntax analysis yet, but just showing you how to do state transition. Okay. Any questions so far?
No.
Okay, now let's add one more thing in. So this buffer 1, 2, 3 is not what we want, okay? So we will do the following thing. Now we will do C in to bar. Before we do C into bar, let's use C out. Enter your string. Okay, enter your string, and then we will C into bar. Okay, so now it's no longer a fixed string. It's actually anything you can input. Okay, so let's don't print now this factor and state. That's too much. Let's actually change the format. Let's use a factor bracket P and then comma. Okay, and then bracket colon for the factor and state. Okay. And this next two, let's actually have some space. Okay, save. Now I'm going to use a terminal. This one will be G++ state.cpp-o state. And that's wrong state, okay? So here that's input space 1, 2, 3 space. Okay, so 1, 2, 3 go to 1. We go to next state 2, and 2 go to 2, and 2 go to 3. Okay, 2 remain on the 2, okay? Any questions so far? Okay. Now let's see. Let's actually enter something else. Let's assume that I enter, let's see, E shell. We see a E. It remain on the state 1. That's wrong. Okay, let's see. So if we are state 1, 0. Oh, here I forget to use the else. So this else is needed. Let's actually open it. Okay. So else. No. Okay, no, wrong. Here else, okay, if ch not equal space. No. So you enter a 0 or a space, you go to stage 3. Okay, so right here, actually, okay, equal 0, equal to 3. And else, if ch not equals space. So the number will be picked up, and then if it's not space, you will also go to stage 3. default, you stay in stage one, okay? So that's needed. Okay, one more time. So you go to the stage three, go to stage three, okay, too many stage three, okay? So if you go to the stage three, let's do one thing, okay? Let's do one thing. You no longer want to you don't want the for loop to continue the loop, so you do break. Okay, you do break, and then right here you will see out finite state machine. Terminated. Okay. You will say your finite state machine being terminated. Let's do one more time. G double plus state, that's CPP dash O state. So let's do state and enter each cell. You have an E go to stage three, you see another E, okay. You see another C and you say syntax error, okay. Let's see, this one actually, okay. If you go to syntax three, you terminate, that's fine. Let's actually do this. Let's do this syntax error and machine terminated. Let's don't put into the stage three. That's actually even in state one. You see this, you already want to break your program. Okay, right here, you want to break your program already. Okay, let's just save one more time. Okay, you see a E, you already have a syntax error. So let's try another one. Actually state, I put a zero or automated two-step syntax error because we only take the natural number. As I emphasize, we only take natural number. So these are okay. So now what we want to do, one more, is that we do have a buffer, right? Buffer actually is your input. Okay, so let's change this one to buffer. Okay, buffer. Okay, let's try another one. Let's actually do string buffer. Okay, another one is called buffer. So right here, we actually read in the buffer, if it is state one, and you are actually read in 1 to 9, your buffer will plus equal the CH. Okay. Okay, so right here, if you are state 2 and have these two, you also have your buffer plus equal your CH, okay, add the later into your buffer. Okay, if you see a space, so here we will say C out, token generated, and then print out your buffer, and your buffer reset to empty string and go back to your normal state. Okay, token generated and go back to your normal state. Okay, so this add one more is that when you have the termination of the token, that happen when you have the series of the number followed by a space, and that space you will generate the termination of the tokens. Okay. One more condition you may generate a token, you don't go to the next state, okay? Is that when you increase the pointer, and if your P equals your actually buffer's size, that means that you go to the end of your string. You go to the end of your string is similar to you read one more of your empty character. So right here, you would actually create a token and go back to state 1. If you actually increase and your buffer, your string always go to the end of a buffer. Okay. Okay, based on this one, let's try, okay. So 1, 2, you go to next day, you generate token 1, 2, 3. You generate go token 1, 2, 3. We start. When you generate token 1, 2, 3, let's see what happened here. That's in your state 2. In your state 2, buffer go to the empty state. You go back to state equals 1. Right here, you are in state number 2. you see a space. Oh, the C, I'm sorry, the C in only, this one C in only read in, C in only read in a single character. That's wrong, okay? So we should use the get S, okay, not using the C in, let's use get S, okay? So this one is to C double plus get line. Okay. So this one we should not use C in, we should use the line of C in and the bar. Okay. So you will not chop, you will not chop at the space. Okay, then you will not chop at the space. So chopping the space you need to avoid. So let's go stay 1, 2, 3, 4, 5, 6. Okay, so you tokenize twice 1, 2, 3, and 4, 5, 6. Is that okay so far?
Yeah.
Okay. Now let's do one more thing. Okay, let's do one more thing. Let's have a vector. Okay, so right here we do have okay, VI tokens. So here, instead of not only to generate it by the tokens, right here, not only generated by the tokens, we also do tokens that push back your buffer. Okay. And this one happen also when you terminate it by end of the string. You also push in the buffers. Okay. And then now let's comment out the stay and next day, and let's comment out the next day, printing of the next day. Okay. We don't need the next day printing anymore. Let's actually comment out is the next day. We are kind of hiding it. Okay. And the token generated, we were also hiding it. Okay, and go out of the loop. Let's do this. Outside of the loop, we do have cout, handle, cout, handle, and then cout. Okay, we actually print out each token from the token list. Okay, so we do successfully token now 1, 2, 3, 4, 5, 6, and 8, 9, 6, 8, 9. Is that okay so far?
Yes.
I think I put it in the wrong location. Should not be inside the while loop. Should be outside the while loop, okay? Because we finish, just do it once after the whole thing, okay? After the whole thing, we just do it once. We don't do it every time when you are in the while loop. So this basically teach you how to create a finite state machine based tokenizer, okay, using C++ language. I try to have more letters and some with spaces, okay, to teach you how everything can be tokenized. Is that okay so far? So each state, it actually read in a token, and then next state, okay? Does that make sense?
Yeah.
Okay. So this teach you a simple state diagram that actually only had 3 states. State 1, standby state. State 2, reading state. State 3, error state. Okay. A simple finite state machine that can process it. So basically, this teach you that later you can have a sequence of the state input going into your finite state machine, and you read out tokens and then token types. Okay, let's look at the token types. Okay, let's look at the token type. So token type right now, we only have one token type. Okay, so here let's do token types. So that's have the VI types. Okay, let's call it token types. And let's have another one called VI types. Okay, so this is token type right now only have one type. This type is number. Okay. Okay, so right here, when you try to add the number into the token, here your token types that push in what? Push in your types 0. Type 0 is number. Okay. Okay, so I changed it a little bit here. Okay. So everyone is a token by number, but you actually tokenize. So later you can add more token type, ID type, variable type, constant type, operator type. And then that can build your tokenizer for the calculator. You want to say? So I just demonstrate you a single stage tokenizer, but later you can build a tokenizer for a finite state machine that's much bigger. Today we don't have that much time to build such a machine. Okay, it's possible that I can write it. I wrote it before, but we do not have the time to finish it within 1 hour to finish this calculator finite state machine. But in fact, you can actually see which one is the termination state and then generate what type of tokens. And the token type are here based on the grammar rule. So when you design a language, you design the grammar rule, draw down the finite state machine, and it's ready for you to write a C program to write a parser, to write a tokenizer for you. That's the whole purpose of today's talk. Is that okay? Hello, is that okay?
Yeah.
And today's tokenizer is pretty primitive, very simple. The purpose is just that you know what is the scanner, what is the tokenizer. But based on that, we are going to develop a much more complicated tokenizer that including parentheses, that including some sort of plus sign, minus sign, pop, push, all kind of operation for calculator later. That's the whole purpose. And then we'll demonstrate that in data structures and algorithms. Does that make sense? Hello, does that make sense?
Yes.
Okay, so that's the topic of the day. Any questions so far? So today we just cover this basic language of the tokenization and talk about simple syntax diagram. Next week, we will go into analysis more. We will go into the prefix and postfix translation and evaluation. And they will also have the so-called translation and the tokenization involved. Okay, we'll go into this postfix infix translation using C++ language. Okay. Okay, if no question, that's it for today. Okay. Thank you. Bye bye.
Thank you.
Bye. Thank you.